What is a galaxy? Well, a galaxy is an ensemble of billions of stars with gas and possibly even some dark matter inside. When we look at the universe, we find a variety of galaxies that come in different shapes, different morphologies. So astronomers use the so-called Hubble classification to classify galaxies within different families. So let's have a look at this diagram over here. On the left-hand side, you see these capital E's that denote ellipticals. Ellipticals are the most massive galaxies in the whole universe. And they come in a sort of round shape. When you move along this axis towards the right end of the diagram, you see that the morphologies of galaxies tend to change. So they become, from round galaxies, you start having these disky shaped galaxies. The very first family that you encounter over here are called lenticular galaxies. Lenticulars are made up of a bulge and a disk. After lenticulars, you will find another type of families that are called spirals. Spirals are called in this way because they are characterized by spiral arms. Our own Milky Way galaxy is, in fact, a spiral galaxy, which is composed by a small bulge at the center, a stellar bulge, surrounded by a number of spiral arms. You can see over here this tuning fork characterizing two types of spiral galaxies. The bottom one shows that these spiral galaxies have a bar inside, and the top one shows spiral galaxies characterized by the absence of any bars. Broadly speaking, all the galaxies that are observed, at least in the local universe, will be able to be fit within one of these families. Let's start with ellipticals. Let me give you a little bit more of information of how astronomers actually characterized ellipticals. So an elliptical galaxy will appear on the plane of the sky like a ball of stars. So a kind of a circle, just like M87 over here. M87 is a special massive elliptical at the center of the so-called Virgo cluster. There are different types of ellipticals. Ellipticals are, first of all, labeled by the capital letter E, followed by a number, E0, E1, E7, and this number is depending on the actual shape of the ellipse on the plane of the sky. So let me give you an overview of this. So you can see over here this is an ellipse characterized by a semi-major axis A and a semi-minor axis B. And then you have this epsilon over here, which is equal to 1 minus the ratio between semi-minor and semi-major axis. Now, according to the type of shape of the ellipse on the plane of the sky, this ellipticity will have naturally different values. For example, if the ellipse were a perfect circle, just like this, what happens? You would have that the semi-major and semi-minor axes are exactly equal. So B equals A. So this is 1. This becomes 1 minus 1 equals 0. So a perfect circle will be labeled by astronomers as E0. Of course, if then the ellipse is squashed in either direction, so it appears like a cigar on the plane of the sky, then this ellipticity will no longer be 0, but it will be from 0 to 7. This number will be closer to 0. So let me show you some examples. Here you have different images of different ellipticals. So you can see the sequence of ellipticals going from the squash one to the perfect circle. So this is how astronomers label the different types of ellipticals. Now let's move on and let's have a look at the second type of family, the lenticular galaxies. Okay? I remind you, lenticular galaxies are broadly described by a central bulge surrounded by a stellar disk. But the main feature distinguishing lenticulars from a Milky Way type galaxy, like our own galaxy, is the fact that a lenticular galaxy usually does not show a clear spiral pattern, while a spiral galaxy will have, like our own Milky Way, clear spirals around the nucleus. So a lenticular galaxy will be characterized mostly by a smooth, structureless, flattened disk rotating around the nucleus. They are usually classified by the capital letter S followed by a 0. Sometimes you will find that there is a capital B in between the S and the 0. So what that means is that the lenticular has a bar inside as well. These are examples of different types of lenticular galaxies. You can see that this lenticular galaxy is seen edge-on. This one and this one are seen face-on. Interestingly, both of these have a bar, but you can see the absence of clear spiral patterns. Now let's move on to define the third family, which is spiral galaxies, like our own Milky Way. Spiral galaxies, of course, they are clearly named this way because they have these spiral arms winding around the nucleus towards the center, and departing from here, they reach the outskirts of the galaxy. You can see that the spiral patterns are defined by different. There is gas, there are sites of star-forming clouds all over the place. So it's a complex structure defining a spiral galaxy. The spiral galaxies are usually denoted by the letter S, followed by small letters A, B, C. These are images of spirals. All of them are spirals, but the tightness of the winding of the spiral arms around the nucleus changes from an SA galaxy to an SE or SD galaxy. So the SA galaxy are usually characterized by spiral arms that are more tightly wounded around the nucleus. And usually, on top of that, their bulges, their central stellar bulge, is also larger than a galaxy, than an SE galaxy. So let's have a closer look at how we define spiral galaxies labeled SA and SC. What is the main difference between these two types of classes of spiral galaxies? The SA galaxies are defined by spiral arms that are more tightly wounded around the central nucleus, while the spiral arms characterizing an SE galaxy are somewhat loose. Now, astronomers need to provide a quantitative measure of the tightness of the winding of the spiral arms around the nucleus, because by doing this, then they are able to assess in a quantitative manner if a spiral galaxy is actually an SA or an SE galaxy. How do we do this? Well, we look at the so-called pitch angle. So let me guide you through this plot to show you what astronomers mean by pitch angle. So if this is the origin of the galaxy, so the center of the galaxy, okay, like think about the Milky Way, for example. This is the center of the Milky Way. This is one of the spiral arms coming out, okay? What astronomers do is that they draw a line from the center outwards, okay? At the point of intersection between this line and the spiral arm, they draw a circle of radius r. At this point of intersection, then they draw two tangents. The tangent to the circle, this thin blue line, and the tangent to the spiral arm, this thin red line. The angle in between these two tangents is called the pitch angle. Now let's see. In an SA galaxy, as I told you, the winding of the spiral arm is much tighter. So what that means is that we expect in an SA galaxy that this spiral arm will be following, it will be closer to a circle. While in an SA galaxy, as I said, this spiral arm will be looser. So what that implies is that the pitch angle will be smaller in an SA galaxy and larger in an SE galaxy. These are different examples of nearby spirals. You can see very nice images, and you can see all these spiral arms. How would we classify our own Milky Way? Well, of course, it is not that easy to classify our own galaxy. And the reason is because we live inside our own galaxy. So it is difficult for us to observe the full spiral structure of our own Milky Way because we live within the Milky Way. It is easier, paradoxically easier, to see a distant galaxy, this full spiral structure, for example, the Andromeda galaxy, rather than the spiral structure of our own Milky Way. However, we do have a number of exquisite measurements of the motion of the stars within our own galaxy, and therefore we can retrieve dynamical information of how the different portion of the galaxy at different distances from us travel around the center. And in doing this, people have come up with a structure that resembles this one. So let's see, let's have a look. This is definitely a spiral galaxy. We do live in a spiral galaxy. Most probably we do have a bar at the center. So it is a capital S galaxy, followed by capital B because there is a bar. Also, the tightness of the winding, I would say, is moderately pronounced. So what that implies is that the Milky Way should be labeled in this way, S, capital B, B. It is very interesting to think about the effects of the so-called projection effects on the plane of the sky. These projection effects could fool astronomers in deciding if a galaxy is intrinsically an E0, for example, or an E7. Think about it. If I have this is a kind of a cigar galaxy, okay? But if I'm looking at this galaxy oriented in this way with respect to my line of sight, I would have no doubts in defining it an E7 galaxy. However, if by chance this galaxy is oriented in this way towards my line of sight, I would be able only to see a circle, and therefore I would naively label it as an E0 galaxy. The chances of these projection effects, okay, are not high. If you think about the full solid angle of a cigar, right, the chances that you are going to see it along this direction or along this direction are quite small with respect to the full solid angle, the full possibilities of rotation of this cigar, right? Interestingly, astronomers observe a high number of E0 galaxies. What that implies is that this large number, yes, some of them might be projection effects, but in fact most of them will be true E0 galaxies intrinsically, because the number is too large to be described by simple projection effects. I would like to conclude this type of tour around through the morphologies of galaxies with the so-called irregular galaxies. What are irregular galaxies? Well, the name already tells us something. Irregular galaxies are those galaxies that do not really fit in any of the classes I showed you so far. They are not really ellipticals, nor lenticulars, nor real spirals. They're just irregular. In general, astronomers divide irregular galaxies into two types: irregular type 1 and irregular type 2. The main difference between the type 1 and type 2 irregulars is on their level of star formation rate. So how much stars they are forming per unit time. The irregular type 2 galaxies are usually starburst. So what that means is that they are forming stars at a very high rate. Vice versa, type 1 galaxies are kind of quiescent galaxies, in which their rate of star formation is extremely low. But definitely both of them have no clear morphology. This is in fact this is the so-called Small Magellanic Cloud, which is kind of a dwarf galaxy which is in the neighborhood of our own Milky Way. Okay, so now I would like to provide you with the very first quantitative measure of a galaxy. As I said, a galaxy is a system made up of billions of stars. One of the very first one of these measures is total luminosity of a galaxy. How do we do this? Well, let me show you. What you see over here is a sort of an elliptical galaxy. Each pixel over here, or each portion of this image, will emit light in all directions. In our own direction, so suppose that we are observing the galaxies at a distance d, and we are positioned over here on Earth. So this small square of area S will emit light that we receive on Earth through the solid angle alpha. Okay? So the intensity of light coming from position X over here and received on Earth will be given by the total flux of the galaxy per unit of solid angle alpha square. So now what we do is that we can rearrange this equation by making use of our definition of flux, which I remind you, flux is defined as the luminosity divided by 4 pi d square. So in other words, the flux that we receive, which is the energy per unit time per unit surface, at a given distance d, the total luminosity, the portion of the energy that we receive at a given distance d, is the total luminosity divided by the full surface area at distance d, which is 4 pi d square. The solid angle, alpha square, is, from trigonometry we know, S divided by D. This is the small angle approximation. And now, if you rearrange this, you divide by D square, you get that the intensity of the light at a given position x is equal to the total luminosity of the galaxy divided by 4 pi s square. So this is the intensity coming, so the energy per unit time, per unit surface area, coming from a point x on the image. Of course, if you want to measure, if you then want to retrieve the full total luminosity of the galaxy, what you need to do is to practically measure your intensity in all points x of your image, and then you sum up all these intensities. In other words, mathematically speaking, you integrate your intensity throughout the full surface of your image. This will allow you to get the intrinsic luminosity L of your galaxy. As you can see over here, for nearby galaxies at least, this is independent of the distance, this equation. You can come up with an intensity as a function of distance from the center. So the distance will be the radius of each annulus that you have defined in your isophotes, and the I is the intensity, the average intensity of that ring competing to that isophote. Astronomers have discovered that all galaxies follow an interesting and special mathematical law in the way the light is distributed around the center. What astronomers have found is that the surface brightness or intensity of the light coming from the galaxy is peaked at the center and then progressively slows down at large scales. So this is distance from the center of the galaxy. Any galaxy is usually more intense, brighter at the center, and less bright towards the edges. And different morphological classes are described by a similar mathematical law, which is called the so-called Sersic law. It's a very, very important and widespread formula adopted by astronomers. Now it's been decades now, the Sersic law, which is characterized by roughly 3 parameters. The intensity as a function of distance from the center of a galaxy is characterized by the first parameter is the intensity at the very center, I0, followed by this exponential profile. Then there is a scale radius, which is usually defined as A, or there are other ways to define the scale radius. And then a parameter, over here an exponent, n. N is the so-called Sersic index. And this n is highly dependent on the morphology of the galaxy. N is usually 1 for spirals, while n gradually increases for more massive lenticulars and ellipticals. It reaches its maximum values, which is around 6, 7, or even 8, sometimes even 10, for the most massive E0 galaxies. So please remember, the Sersic law is one of the fundamental laws that, or parametrizations that are used by astronomers to define the galaxy light profile at least in the local universe. As I said, once you have measured your intensity as a function of distance from the center, then you can, for different isophotes, then what you simply do you can mathematically integrate your surface brightness and retrieve your total luminosity, the intrinsic luminosity of the galaxy. That is the physical quantity we are after at the end of the day. So if you want to integrate a surface profile, you need to have some sort of mathematical formula that can be included in your integral. So you plug this inside your integral, and here you are integrating between 0 and infinity. So from 0, 0 means from the very center of the galaxy to infinity. Infinity means basically to very, very large distances. And if you do this and you integrate, you will find that the total luminosity of a galaxy at the end of the day is characterized by two parameters, which is the central brightness and the scale radius A. So you can measure these two quantities directly from your fitting of your images and retrieve the total luminosity of a galaxy. Now I'm getting towards the end of my lecture, and I want to introduce you to another very important galaxy property, which is the overall velocity of the stars, the average velocity. So in other words, the quantity that answers the question, do stars move within a galaxy? In order to answer this question, we need to distinguish the different morphological types, because the type of motion of the stars will be different in different galaxies. So let's now talk about two families, ellipticals and spirals. In elliptical galaxies, remember, the elliptical galaxies are the galaxies that show us balls of stars. Now, in order to be balls of stars, the motion of the stars around the center of mass of the galaxy, is disordered. So what that means is that the stars move in all directions in this ball. Vice versa, in a spiral galaxy, the motion of the stars is quite ordered. So the stars will move orderly in patterns, in circles, right, around the center. So there are very different types of motion that characterize of stars that characterize an elliptical and a spiral galaxy. So let's start with ellipticals. How can we measure the average random velocity in the random motion of stars in an elliptical galaxy? The way they do it is through spectral features. So I remind you, the spectrum of any source in the sky is a diagram, a plot of the intensity of the light as a function of frequency. And the different features of this spectrum reveals a lot about the structure and composition, and as well as the dynamics of the source. With respect to dynamics, we look at the absorption features, the absorption of light, so the dips in the spectrum of a galaxy. We believe, astronomers do believe, that that absorption, this is the absorption feature of an elliptical galaxy. Astronomers believe that this absorption feature, this wide absorption feature that you measure in the spectra of elliptical galaxies, is produced by the convolution of the absorption features in the spectra of each single star in the elliptical galaxy you're observing. So each of the single stars that is moving in all directions, okay, in respect to the center of mass in the elliptical galaxy, causes a sort of Doppler effect in the absorption within the galaxy. So, for example, a galaxy that is moving in this direction will produce an absorption feature that is displaced with respect to the center of mass in this direction, and vice versa. Then you sum up all the absorption features in the atmospheres of the stars of each single galaxy, and the convolution of this will create a huge absorption feature in the spectrum of the full elliptical galaxy. By measuring the full shape of this spectrum, astronomers retrieve a quantity which is called velocity dispersion. In other words, the average velocity with respect to the center of mass of the stars in the galaxy. It's a very powerful measurement. So this is a full galaxy spectrum. So this is intensity, number counts as a function of wavelength, okay, or frequency. And you can see this is the spectrum. You can see all these absorption features that derive from the fact that the light along the line of sight is blocked. As I said before, in a spiral galaxy, the movement is circular. So you don't have a disordered motion. So you don't have stars moving around with respect to the center of mass. They just preferentially move in two directions, in this way and in this way. So an observer, okay, over here will receive, in this case, a sort of emission line coming from these stars, and it will be blue shifted or red shifted depending if the source, the stars, are approaching or receding with respect to the receiver. So what that means, the average velocity of the stars around the center of mass. So this is a full rendition of what I just described. So these are the actual measurements. They are quite complex to describe. This is so-called integral field spectroscopy of the images of galaxies. So in other words, you take the image and you do the spectroscopy per pixel in the image of the galaxy. This is a very powerful technique that allows you to get the average velocity of each pixel in the image of the sky of the galaxy. And you can see that for an M87, for an elliptical galaxy, like this one, the stellar velocity is just a mixture of blue, yellow, green, and red points. So the color coding here means receding or approaching. Blue is approaching, red is receding. You can see that in the case of M87, you don't have any clear pattern. And the reason is because M87 is a pure elliptical galaxy, and so all its stars are moving in all directions, and therefore you see all these colorful dots that show you that there isn't any clear pattern there, but the stars are moving wherever they want to move, in essence. While instead, for an S0 galaxy, which is characterized by a disk, most of its dynamics is driven by the motion of the disk, you do see a clear pattern over here. You have the red wing and the blue wing. So this is receding from us, this is approaching us. And this is the reason why you do see this clear bimodality in color of the galaxy. So I would like to stop here